Yeah. Cool. All right, I think we should make a start. We'll, talk of the day before we have a bit of a wrap up. So it's going to be by Rebecca on recent advancements in Bayesian record linkage.
Thanks very much, Robin, and thanks to the organizers for having me. It's really great to be here. So I'm going to talk about some very, very, very recent advancements in Bayesian record linkage. So mostly from 2011 and moving forward. So I really do mean recent. So this is a lot of joint work, and so I'll give the references as I go along. I want to give a couple of motivational examples based on some things that I work on. This picture, the credit is completely given to Brunero Liceo, who's worked so much in record linkage. And it's thought to be one of the very first drawings of record linkage by Bruno De Finetti. And so what it represents is E-stat here, and some different thinkings of how different local families, in terms of going back and forth to the community, and different types of databases, here with the postal service, the telephone, water, electricity, and then other ones involving sanitation, and then here regarding vehicle registration, as well as involving vehicle registrations, and so lots of different, also with banks, and different databases, and how thinking about how these different databases were working together very early in terms of Italy. And so one of the questions we still have today, and that many people have talked about, is how do we actually cope with duplicated data in administrative records? And so anyway, I thought it's quite interesting, this very early drawing by De Finetti. Another very prominent problem that others have also touched upon is in precision medicine. So at least in the US, dealing with sepsis or septic shock is actually the leading cause of death. And so this is a $3 trillion problem. And so this is one of the applications that I'm working on with some biostatisticians at Duke University. And so how one of the questions is, how can we deal with duplicated data within and across health databases so that we could understand how patients are deteriorating over time. And so this is what Peter mentioned as dealing with relational data. And so we can kind of think of this as a graphical modeling or even a networks problem. And then the third one that I'll give, and so this is the problem that I probably spend the most time thinking about, and that keeps me up the longest at night, is how do we cope with duplicated deaths, for example, in the Syrian conflict, or just in matters of human rights violence. So in many different human rights violence, there's duplicated deaths across and within these different databases. And in terms of bringing dictators or those who are creating the violence to justice, one thing that is needed is trying to understand what is the actual death toll and what's a standard error or a measure of uncertainty associated with that death toll. And so these are problems that different human rights groups have been working on for more than 20 years, and something that those at Duke have worked on, as well as at Carnegie Mellon. Okay, so common themes in the data here. So these three different illustrated real examples have both duplicated data and are going to require record linkage. And so this is just a very simple illustrative example of what record linkage looks like to me, in terms of thinking about, here are two duplicated entries in red. They have similar information, but it's slightly different. And here I'm just assuming that all of the other individuals are actually just singleton entries, and they're all different from everyone else. And so this is a kind of just a very simple example here. So we've talked about record linkage some, mostly I think more about record linkage and how it interfaces with privacy. But record linkage is joining together multiple noisy databases to remove duplicated information, and often it doesn't have unique identifiers. And typically we do this to answer some question about inference or some underlying other question. Record linkage is also, it has many other names. It's known as entity resolution, de-duplication, coreference resolution, depending on where you're coming from in your background. And there's many different applications, and because of the increase of streaming data and big data, it's become more of a need for record linkage has become more pressing in the last decade. So examples are the ones that I started with, but also include things like credit fraud, investigative journalism, and also genetics, and there's many other examples. Okay, so this is how I think about record linkage as just a bit of a cartoon example. So we have maybe 3 different databases. So I'm going away from this 2 database example. So I'm thinking about the fact that we could have k different databases. So here I'm just thinking that we have 3. They're large. So we have Apple, Amazon, and Google. And then I'm thinking about that we could have duplicated information across and within each database. And then I'm thinking about here, so I have different nodes, and each node is represented as an entity. And for each node, I'm representing an entity by the person's name. So here I have a node with Larry Wasserman. He's a person, he has an address, he has an occupation, he has maybe 2 cats, and perhaps his favorite color might be purple. And then I have someone named Steve Feinberg. So I'm going to pick on my postdoc advisor since he's not here. And so Steve here, we might want to know, is this Steve Feinberg the same as the other Steve Feinberg? And so if they are the same person, then we're going to draw an edge here. However, this Steve Feinberg may not be the same as the other Steve Feinberg, and so you can notice that the I and the E are switched. And so here we're questioning this placement of this edge. And so to understand if these 2 people may or may not be the same, then of course we need to look at their features or attributes. So how do we do this? Okay, so this data is actually publicly available online. So here I'm looking at one Steve Feinberg that lives in Pittsburgh, Pennsylvania. He has an age range. He also has a phone number. And then I'm looking at a different Steve Feinberg. And so if we just do these as a human matcher, we can see that these Steve Feinbergs would not be the same person. And we want to build some sort of method or algorithm that would say that these 2 Steve Feinbergs are not the same person. And so we'd want to remove that edge. And so then we'd want to do this also with the same data set that I'm working with for Syria. So I wanted to give a motivational example with the toy data set, but this is the data set we're really looking at, where these 3 individuals have similar types of feature information. The names are in full Arabic, and we have duplicated deaths within and across the databases. And then we have different information based on these Syrian individuals that were found to be dead in the Syrian war. So we have things like date of death, a high-level location where they were killed, as well as their gender. And so here we find that these 2 individuals are the same person. However, these 2 individuals are not the same person. And so this gives you an illustration of the setup each time is exactly the same. Okay, so now let's talk about a little bit of the evolution of record linkage. So as I said, I'm going to talk about more recent advancements. So Peter did a really nice tutorial and introduction into where kind of things started, as well as where the CS community has gone. So I'm going to review a little bit the Foley-Sunter method, which originated actually in genetics in 1969 by merging together different genetics databases, and this is still a very pressing problem today. And then between the periods of about 1980 and 2000, there was a really large giant focus in health, government, privacy, as well as Bayesian methods. So a giant surge here. And then in about a 16-year period, there was a large surged then by Bayesian methods, machine learning, and clustering. So for the rest of my talk, what I'm going to do is I'm going to review, at least in my opinion, the two most standard methods that I see that are used today, and these are methods used by statisticians, social scientists, psychologists, so all over the board. And then I'm going to introduce some new Bayesian methods that you may or may not have seen, and then I'll finish talking about some open challenges and research problems. So the two most popular methods today that at least that I see, the first one may be surprising, or maybe it's not surprising to you, is actually hand matching. So I see this a ton even when I referee. And then the second one is the seminal method of Fogge and Sunter. Okay, so the first one, hand matching. So here we're assuming that we simply just have two databases. This is just a simplistic view on hand matching. There's more complex approaches. And then you simply take any two records in this database, I and J, and then you look at them if I'm the hand matcher, and I use my subjective knowledge to say if these two records are the same or not, and then I label that as either a match or non-match. And then perhaps maybe Peter is also going to do the same thing, and Peter will use his subjective judgment to record whether it's a match or a non-match. And then perhaps maybe we have a third hand matcher, and so maybe that's John. And so then John is the third hand matcher, and he labels it as a match or non-match, and so we can maybe all see the problem that starts to happen then as we use our subjective judgment, and then maybe, you know, as we go along, our subjective judgments may vary from person to person, and also you get tired as you're making these assessments, and so there's a lot of different problems going on here. So one of them is just first the scalability, so going through these is incredibly slow. Doing this over and over and over again is also very costly. And then personally I like talking about uncertainty and error. So what is the error in this process? This is very difficult to articulate, as what is the error in a hand matcher? But this is something that's still very much used today, and it's often used in building training data. And then there's the seminal method of Fogge and Sunter. This was also proposed by Newcombe and his co-authors from 1959. And so this is where you have two different databases. You have records within each database. Here you're doing all-to-all record comparisons, so this is computationally not tractable. And you're looking at a likelihood ratio test when you're doing this comparison here. So what you're doing is you're doing a likelihood ratio test, and based on that test you're deciding whether those two records are either a match or a non-match based on a threshold T. And so that threshold T is very arbitrary. So as I mentioned, this is computationally intractable. One of the main issues that many people have with this as well is the fact that transitivity is not preserved. So what I mean by transitivity is the fact that if record A matches to record B and record B matches to C, then it's a transitive closure if then that C matches to A. And it's well known that with hypothesis tests and Neiman-Pearson tests that transitive closures don't happen. There's not a necessarily easy way of making that transitive closure happen. And so here's just one plausible way down here of showing that here if 1 matches 2 and 2 matches 3, then 1 does not necessarily imply that 1 has to match 3. And so there's major limitations and major flaws regarding if you would like to have a 3-way transitivity, a 4-way transitivity, things of this nature.
Why is transitivity desirable? Because I've heard the saying that you can change your name on the fly by saying that each letter in turn is a spelling mistake, and that seems like you should stop matching at some point.
So, I mean, transitivity, at least for me, is desirable because you're saying, if the method is saying that this record is matching to this record and this record is matching to this record, and you're wanting to do some sort of inference regarding the fact that all of these records match to each other, and you're wanting to propagate some uncertainty about this particular matching, then not having this relation becomes incredibly problematic, and you have to come up with some decision process here. So possibly another way to put it is you have to, so suppose you don't care about transitivity, then you're going to have to choose one of these choices. And so which one do you choose? Which one is the right one? And to me, that's not clear. Okay, so let's move away just slightly from the seminal paper to look at one extension that was recently done and was really very nice. One of Steve Feinberg's students, Mauricio Sedinli, who's doing a postdoc with Jerry, wrote a really nice extension to allow for transitive closures, and specifically K transitive closures in a Fourier center framework. And so this appeared in JASA in 2011. However, one of the main issues is the fact that it's not scalable after three databases. So in terms of practical usability, it has a lot of different flaws here, even if you impose something like blocking. Okay, so when I think about big concerns in record linkage, I kind of break them into two categories. I think that most record linkage methods alone are not scalable, and so we'll talk about that just for a moment. And then what I want to spend the most time talking about is what is the underlying question of interest. So that's what you should start with, and that's, at least to me as a computational social scientist, what I really care about. So in terms of scalability, I think we would hopefully all agree that we need something like blocking in order to make our methods scalable. So blocking, just as a quick review, if we consider the red space, then here we're doing all-to-all record comparisons where I'm just considering two databases. So here what I'm considering in the red space here is I have a database 1 on the left, and on the bottom panel I have a database 2, and so I'm considering the pixels inside as literally every record comparison. And so the red is saying, okay, well this is really bad. I'm wasting a lot of computational power, and specifically if I have n total records, then the order here is n squared. So what can we do that might be a little bit more clever? Well, if records are similar in some nature, then we could place them in what we call blocks, partitions, bins of that nature. And then they might look in this form, and it doesn't have to be block diagonal, it could be in any type of form. But here you'll notice that they have a nice structure where they're not overlapping. And so if they're not overlapping, then you only have to compare within each partition or block. And so you can make everything completely parallelizable, and you gain the computational cost that's gained now is now in the green region, and the computational region that you're only having to look into now is in this much smaller red region now. And so you're only having to perform your record linkage procedure within the red region. And so Peter talked in his tutorial and also in his talk a lot about advanced blocking methods. So I'm not going to go into that. There's a recent review paper that I worked on with Mauricio, as well as Sam Ventura and Steve on recent blocking methods. So I'll give that as a reference. And then move on to the second question. So depending on what you're working on, the main question I think should be, well, what is the underlying question of interest? And so that could very much differ depending on if you're working in academia or government or industry. So often in industry, you just care about a point estimate. So I get a lot of calls maybe from startups of how should you do some type of record linkage? What should we do with our data? So as a specific example, maybe I'm someone from Amazon and I just care about these different prediction type schemes of what you see when you go to Amazon, and I want to do better preferencing. And they could care less about the overall type of uncertainty, but they want to get it somewhat right, but they don't care about measuring the uncertainty too much. And so the why is they're Amazon, they're a big company, they need really quick answers, and they need to keep on moving. And so the solution is they use things like random forests or some type of semi-supervised learning. And so if you just care about point estimates and you don't care about uncertainty, then maybe you want to do some sort of semi-supervised learning method. Okay, but what if you actually really care about the uncertainty and you really care about propagating that error? So just as an example, suppose I want to estimate a death toll from the Syrian war. And I really care about how much I'm off, because that really matters. So it really matters if my death estimate is 191,000 versus 250,000, and it really matters what the standard deviation and that distribution might be. And so the United Nations also very much cares about this, as well as, well, they claim to care about it, as well as, but the human rights groups really, really, really care about getting this precise and right. So at least my take on this is that you should be Bayesian in nature, and I'm going to assume this case today in trying to explain to you why I think that this is the right approach. So the Bayesian literature, in terms of what had been previously done, is specialized to very specific problems. It deals with two databases. In terms of extending them to more than two databases, it's very difficult to extend this past two databases. The methods, however, do, though, give exact uncertainty from the record linkage process, which is a really, really, really nice point from the Bayesian paradigm. However, these types of approaches that I'm listing below don't easily generalize to what I'm calling multiple record linkage. So this is where you're trying to merge together k different databases, and you're wanting to simultaneously update everything at one time. Also, a lot of these methods don't scale particularly well. However, there's some really nice insights, especially from two of these papers. So one by Tancredi and Liceo, of taking a really interesting way of looking at a mixture model, as well as taking some previous ideas from Kobus and Hulton from 1990 of looking at ways of distortion. And then there's a really nice approach from Gutman from 2013. So Jerry mentioned that a little bit. I'll mention a different aspect that I really like about that paper more. And so those are two papers that I think that are kind of really nice advancements in the two-file scenario that a lot of work can be built upon. So specifically in the Gutman paper, they called for what they say are these more sophisticated network data structures, and they were a bit vague about this. But looking back as well on the Tancredi and Liceo paper, they used what's called a coreference matrix. And so what this does is they're clustering records to a latent type of entity. And so I'll touch on that with some pictures in the coming slides. And so what I'm going to talk about is some recent work of Mauricio Sedinle, some work that I did with a PhD student at Carnegie Mellon, as well as some a very large collaboration with some members at Duke, as well as Microsoft Research, where we work with these more sophisticated data structures so that you can look, so that you can explore the high dimensional space of the parameter space. The really nice thing is you can propagate the error of the linkage procedure exactly. You can then integrate the results into any analytic procedure after that. So for example, you could do logistic regression or capture-recapture, or any type of method you would want to do, and you know the linkage accuracy exactly. So the common idea of all of these papers is you're going to take similar records, and you're going to cluster these records to a hypothesized latent entity. So the idea is this latent entity is dropped down from an oracle and it's unknown. And so then it comes from some distribution. And the question, underlying question that's been really hard to answer is what distribution should that latent entity come from? So let me show you some pictures of, more graphically, of what this looks like. So we're going to link records to what I'm calling latent individuals or latent entities. So back to my toy example, it looks something similar like to this. So instead of doing all-to-all record comparisons, and instead of just looking at 2 databases, we're going to look at all K at one time. So here I'm just looking at 3, but you can look at all of them. And then I'm going to take the Steve Feinbergs that are the same, and I'm going to cluster them to a latent entity that I'm calling S. So it could be called S, it could be called Steve, it could be called 1, it could be called anything. The labeling doesn't matter. And I'm doing this via some model, and I haven't told you what the model is yet. And then I'm going to do it again. So now, when I was at Carnegie Mellon, I had a colleague named Ryan Tibshirani, and his father's Robert Tibshirani, and they would commonly get confused because they're both statisticians. And so the idea is to cluster all of the Ryan Tibshiranis to a latent entity. And you don't want Rob Tibshiranis to get into the same clustering. And so if we think about this, we have this problem in human rights and official statistics and all types of data problems. And so you need a really clever model to do this. And so you're going to keep doing this over and over and over again. Okay, so there's a generalized literature now that takes similar approaches to the picture that I just showed you. So it's doing this general type of approach where you're clustering the data to a latent entity, and then you have these edges here. And these edges are known as what we call either a linkage structure or a coreference matrix. And they're the same thing. So you can show, it's been proven in a paper that the construction is the same thing. And so I'm going to walk through some of these different papers and show some advantages and disadvantages of the literature and how it's been moving forward. Okay, so the first paper, the reason that we started working on this, so this is a paper with Rob Hall, who's now at Etsy. He was a PhD student at CMU, and also this is joint with Steve Feinberg, is we started working on this because we wanted to be able to merge together for the first time K different databases and take into account simultaneous record linkage across the databases as well as de-duplication within. And the main thing we really wanted to get at as well is propagating uncertainty. The thing that we assume in this paper is we assume that the records are noisy. So we assume that they're corrupt, degraded, there's typographical errors, and we want to decode that through some modeling process. So we have this novel representation, which we call the linkage structure, which that's the edges from the picture. So we're clustering records to a latent entity, and then the linkage structure is keeping track of who's who. And then through the linkage structure, we can run a hybrid MCMC. So we can do something like split and merge. And so we can efficiently run through a high-dimensional parameter space using a hybrid MCMC. Also, one of the really nice things, if I go back to this picture, is that at just at each one iteration here, transitivity is completely preserved because we have a bipartite graph. And so while it's very awkward in a frequentist or Follagy center type of probabilistic approach, it comes out completely naturally here because of the bipartite graph. And extending that in terms of over all Gibbs iterations ends up being not very difficult.
What's your number of parameters in your Bayesian model? Because the depending on how many groups you have.
I'll show one of the models in a moment. So it allows for, this method allows for Bayes estimates to be easily derived under a squared error loss in a principled way, so you're able to get a Bayes estimate exactly. And we're also able to get uncertainty estimates of these records that can be propagated then into later analyses. And so this is all in a package, and I'll link to the package in a moment. Okay, so one of the shortcomings of this initial model was that we only allowed for categorical data. So when I extended it in this paper, it handles both string and categories. So it handles both categories as well as continuous data. So here what we do is we assume that, okay, given some sort of true latent string, what's the probability of that observed string? And so all we're doing here for computational convenience is we're taking the empirical distribution function, and then we're multiplying it by a normalized density of taking any distance metric, and we're looking at the distance between the observed string and the latent string. And so this is built in the package for Jaro-Winkler, for edit, for many of the common distance functions. So the x's are simply just representing the data, where I is indexing the number of databases, j is embedded in there, the number of records in each database, and then L is the number of features within each record. So we have three things in terms of indexing going on here. So we're measuring everything at the actual feature level. So the y's are actually the hypothesized latent entity, so this is what's getting dropped down from the oracle. So the records are getting clustered to this latent entity. And then we're going to link this using the edges by the linkage structure. And then Z is simply just a notion of how much noise we have in the model. And so these are the main parameters that we're modeling. So in terms of the actual model, so we have a weight that's alpha L of W, and this is simply the relative frequency of the observed word in the data for each particular feature. So again, we're doing everything at the feature level. And then GL is going to represent the empirical distribution for each feature. So here, all I'm giving is that if I have a categorical, if I have a string valued variable, then I'm going to multiply it by how often it appears in the data, and then I'm going to normalize it by this distribution, and I'm going to look at the distance between the observed word and the latent word. And so I can look at any arbitrary string distance here. Okay, and then comes the generative process. So if there's no distortion, then the record is simply just the same as the latent quantity. And then what we do is if we have simply a string valued feature and we have distortion, then we take this from this distribution here. So we're actually going to compute those distances. But if we have some sort of categorical valued variables that we don't think are too noisy, such as gender, that we know from a domain expert, then what we're going to do is we're simply going to draw these from the empirical distribution function. Since these distances are quite, these are the most computationally demanding to fit. And then for the latent quantity here, what we draw from here is we take this again from the empirical distribution, and the motivation here is again for computational efficiency. So this is an empirically inspired type of model. And then for the choice of the distortion component, we're taking this from a Bernoulli distribution, so it's basically just a coin flip where we're tuning the amount of distortion based on a beta distribution. So the amount of distortion that you have in the model will be determined by how concentrated your beta distribution is. And then what I think is the most interesting part to look at, and I'll talk about a bit more, is this distribution on the linkage structure. So what we did at first is we put a discrete uniform here from 1 to the total number of records. And so the main motivation for this is to put something that is a bit flat and ends up not being so flat in terms of in terms of inference, from what we eventually looked at. But it was very difficult to say at first what should be the most subjective prior to put on the linkage structure here for every choice of I and j. And so this ends up being a very difficult question in general.
Remember IJ is the bipartite graph, right?
The bipartite graph it's actually more complicated than just the lambda ij. So the bipartite graph, it's looking at the records. So the records are each of the nodes, which are the data points. The latent entity is here, which is the y. And then what's creating the part that's bipartite is that data structure that Gutmann was calling for, which is the linkage structure.
What are the two node subsets that make the bipartite graph?
The I and the j.
The lambda's an adjacent matrix.
Sorry?
Lambda's an adjacent matrix? Sorry.
Yes. Lambda can be.
That's what I meant.
Okay, that's what you meant.
Yeah.
Sorry, John. Yeah. And then the coreference matrix that I'll get into of CD and Lay can also be written as an adjacency matrix.
Technically a bi-adjacency matrix, right?
Yeah. Okay, so as I mentioned, there's a very clear connection that can actually be made between a paper that Mauricio Sedinli wrote that applied in the Applied Annals of Statistics, where he refers to the data structure as a coreference matrix, and what we call a linkage structure. So you can show that the coreference matrix is a special case of the linkage structure. So you can actually go back and forth depending on what representation you like. One of the main differences is Mauricio's approaches, he doesn't actually go down to the field level of the structure. So he never has the features L, he just works with the actual records. So due to this connection, you can actually think of the two different data structures in exactly the same way. And so they can be written in the same type of formulation. So I'll refer to them as the linkage structure, but they're the same. So what are some advantages of this method? So the method works, it tends to work well in practice. So we looked at this for two different real data sets as well as a synthetic data set. One of the interesting things is that it beat the false negative rate as well as the false discovery rate, or the precision and the recall, when we compared to random forest, Bayesian adaptive regression trees, as well as logistic regression when the training data was 10% or less. So when you have a very small amount of training data. And so for a lot of real data type of applications, such as human rights conflicts, you have very, very, very low training data. Or in some examples, you may not even have any training data. And so this was kind of an interesting, this is something that we didn't expect to find. And so we have the comparisons in there for higher training data, and the method does just as well, for example, as random forests and BART in these situations when you have, for example, 50% training data. I think the idea is pretty simple. The math is, in terms of the indexing, is complex in terms of keeping track of things, but I think in terms of the pictures is a pretty simple idea to come up with. This is just an example of a simulation study using the record linkage package, the RL data 500 data set. Of what we did is we assumed that we didn't know the ground truth, and we ran our algorithm on this data set. So what it consists of is German names and full date of birth. And so what we looked at is we looked at recovering the posterior distribution, which is in black, as well as estimating the false negative rate and the false discovery rate, which we both were able to get very low at 0.04 and 0.08. And then we estimated the posterior mean and standard error at 452 and 7. And so they're both so the posterior mean is very close to the ground truth, which is at 450. So the method is pretty accurate in terms of recovering the actual ground truth when you have unique identifiers and you can check the results. So what are some disadvantages? There can be extreme issues with mixing due to the high dimensional parameter space. So this isn't a flaw per se with our method. This is a flaw with MC methods in general and also with clustering. So this happens just in general and something just to be aware of, that you can have mixing issues where things can get stuck in local modes. And so one thing that can be helpful to do is to kind of boost your method with something like a semi-supervised method, like a random forest, for example, to try and help yourself get out of a local mode. One thing that is a disadvantage is the fact that it is very sensitive to the hyperparameters in the model. So for example, the choice of C and A and B, it is very, very, very sensitive to those values. Also, what we found for the method of Sedinlay and AOAS, as well as our method, the uniform prior on the linkages is incredibly informative. And so what I mean by this is if you look at the marginal distribution of the linkage knowing the truth, suppose this is the truth, then the actual prior should be about here, and try different colors. So one marginal prior ends up over here, and the other one ends up way over here. So the conclusion from this is the fact that while you're putting something that's somewhat uniform on the space, if you know something about Bayesian methods, uniform priors are not flat and they're not non-informative. And so what it's doing is it's putting something very, very, very informative on the space, and so you need to do something else. And so I'll come back to that point in a moment. So I want to highlight some of Mauricio's work, especially since he's not here. So there's been a lot of interesting work done by Mauricio. He's on the job market this year, and he's become very much an expert in record linkage since doing his PhD. So what he assumed in a recent paper in JASA is he assumed that there's two databases and no duplicates within a database. And then what he does is he assumes the data is always compared for the full record. So again, he doesn't always go down to the feature. And he derives very principled base point estimates of the linkage structure, which he calls the coreference matrix. And so this is an extension of Mauricio's from his thesis, which didn't actually address this issue. And so what does Mauricio do here? So he has I think 3 really strong advantages here. So it greatly outperforms Felly-Sunter mixture models in terms of their actual error rates, and he shows this on many different simulated data studies. He also derived many different Bayes estimates for a very large class of loss functions, which means you can customize this approach to particular applications. So for example, if you care about a false match more than a false non-match, then you could customize this approach using the particular loss function that might be more appropriate here. And under some general conditions on the loss function, the Bayes estimate has a closed form. So this method is very, very, very general. In terms of some disadvantages and maybe some things that Mauricio is working on, it relies on existing blocking methods which scale to large databases since it's working with pairwise comparisons of records. I think many different methods, though, have this particular disadvantage. Again, it doesn't directly model the covariates in the databases. I don't know that there's a giant consensus of whether it's better to work with the features or with the records, so I think that's more of a personal preference of the researcher as well as maybe possibly the institution. And then I think one of the things that could be worked on and extended is assuming It assumes 2 databases and there's no duplicates within each database. And so I think this would make it something that would be more usable and more pragmatic. But in general, it's a really nice paper. Okay, so kind of coming back to this general problem over here of the prior and the linkage structure and the fact that it's too informative, I'd like to talk just really briefly about what should the prior on this linkage structure be. So this is something that I've spent a lot of time thinking about, and my claim, and hopefully I can convince you of this, is it should not be something like a Dirichlet process from Bayesian nonparametrics. And in general, it shouldn't be any type of infinitely exchangeable process. And so what this does is it raises really deep and interesting questions about certain types of high-dimensional clustering tasks that directly apply to record linkage. Okay, so I just want to kind of explain the motivation and what I'm talking about when I'm talking about doing a different type of clustering and how this relates specifically to record linkage, and then I'll give you an example of what I mean by this. So the goal here that I'm thinking about is I'm going to cluster n data points, and so here these are records, into k different clusters. And so this is just a very naive example. So here I'm clustering 41 records or data points into these 3 clusters. And so the way that I'm going to think about doing this is very differently from the way that the record linkage literature has dealt with this before. So what I'm going to do is I'm going to place a prior over partitions, what I'm going to call bracket n, and this is going to go from 1 to n. And I'm going to let C sub n represent a random partition of n. And then this random partition can be represented by a set of cluster assignments from Z1 to Zn. And so what I'm thinking about here is that I have actually 3 different clusters here which are colored. And these are known as clusters, classes, or blocks of a partition. And these blocks shouldn't be confused with blocking and record linkage. So the block terminology here is something that's specific to Bayesian nonparametrics. Okay, so the 3 clusters might be something like cat, dog, and mouse, just to be very simple. And so the random partition then would simply just be saying, okay, these particular records which correspond to cluster 1 or dog are in this random partition Cn. These red data points here correspond to the cluster assignment cat, and then these purple data points correspond to the cluster assignment mouse. And so this is just an example of what the random partition looks like. And so the clusters have different sizes, which are 10, 15, and 16 here. And so I'm making a very big assumption that I also know the exact random partition, and so I can recover it. Okay, so where am I going with this? So if I think about what classic clustering does, and I want to try and tie this in with building a prior here, many clustering tasks are assuming that the cluster sizes are growing linearly with the size of the data set. And so if I think about what record linkage is doing, if I think about the actual size of the clusters, these aren't going to grow linearly with the size of the data set. In fact, they're going to grow negligibly compared to the size of the data set, or sublinearly. And so if I think about classic examples of clustering processes, these are going to be Dirichlet processes or Chinese restaurant processes. And so these aren't going to be appropriate for the types of priors I would want to put on my linkage structure. So what these types of processes tend to do is they exhibit a richer get richer behavior of many different clusters with many different data points in each cluster. And if you think about record linkage, typically we might have many different data points, but a few, or many different clusters, but a few different data points in each cluster. So how do we go about handling data where we care about the exchangeability of the data points, but also as the number of data points is growing, the size of each cluster is negligible? So how do we handle this? So what I claim is we could do something that I'm calling microclustering. So what we can do is we can have a sequence of random partitions, C sub n, and this can exhibit what we call the microclustering property if the size of the largest cluster, M sub n, is of order OPN, meaning eb sub n over n is going to 0 almost surely. And so what this means is that we can define a clustering model that exhibits the microclustering property if it's implied by the, if a model that we define satisfies the above definition. And so here's an archived version of what we define to be this microclustering property, as well as a model that satisfies this property on some preliminary data. So let me just finish with three small points. So one thing, so the 2 points I'd like to show here is that specifically if I consider a Chinese restaurant process or a Dirichlet process, suppose that I increase the number of data points, but I hold the concentration parameter fixed. Then what happens as the number of data points is actually increasing here, then what I find is that this isn't going to be appropriate for microclustering because the size of the clusters is actually increasing. So what's happening here, especially as the tail is going out, as the clusters here are increasing. And so if we think about record linkage applications, then the clusters, in terms of the empirical distributions, are quite strange looking. So the actual empirical distributions might look something like this, but they often have a strange tail out here. And then the other thing that's quite interesting to look at is suppose we actually vary n and alpha jointly. Then what happens? Well, in the extreme case out here, we actually see that the CRP becomes less and less flexible. And so what's actually happening is the CRP is collapsing on a one-parameter family. And so if we think about record linkage, we need something that's going to be incredibly flexible. And so if we have a model that's collapsing on a one-parameter family, and we're wanting to put something like a CRP, especially on something like the linkage structure, then it's not going to be able to capture something that has a lot of different dependencies and a lot of different complicated structures. Okay, so I'll just finish quickly with some kind of open questions. So what is kind of a principled way of modeling the linkage structure or the coreference? Let me finish with this one. So what's a principled way of modeling the linkage structure or the coreference matrix? So I think maybe a promising way of doing this is with microclustering. What are some scalable ways of potentially doing record linkage? So in our archive paper, we have what we call a chaperones algorithm, which is similar to a split and merge type approach, but it has a very general proposal type algorithm. What are some good approximations when MCMC fails for record linkage? So this is a very, very, very open question, and I think one that could use a lot of help answering. We need computationally scalable methods for synthetic data release, as Jerry talked about and Jerry's working on with a lot of his students. And then one thing that I've been working on and thinking a lot about is, can we have a protocol for PPRL where the error actually propagates and it propagates exactly? So could we have something not just for 2 databases but for K databases where in step 1 we do some sort of private blocking like min-wise hashing, and then we take those records and we do some sort of Bayesian procedure where the error propagates exactly, and then we're able to do private evaluation and an exact error propagation all the way through. So I'd like to thank the different foundations that fund my research, as well as the Human Rights Data Analysis Group for providing me with data. And I'm happy to take any questions.
Are there any questions, comments? Talk?
If I hand your GitHub package to a team of researchers well-trained in Filegi-Sunter, how long will it take them to do a real example?
So if you hand me a GitHub package
Hand
for,
your GitHub package to people who are experienced users of Filegi-Sunter. But ask them to do record linkage using your package.
using my package, how long will it take it to run, or take them to use it, or all of those? How big is the-
assignment to the production of a result?
Okay. I mean,
Without you.
without me,
20 minutes?
This is called the Bill Winkler problem.
sure. Well, it depends on how big the data is. So give me a
300 million.
300, so the census,
Of course.
of course.
Why should I give you an easy problem?
You can block.
Well, of course you can.
Yeah, you can block.
That all requires all the same
Yeah.
judgment and experience
Of
with the
course.
methods that
course.
has been accumulated with Filegi-Sunter. That's why I'm asking.
The question is, I'm not sure, but different people have used the method and had no problems using it without asking me questions.
That's fair.
So,
So that's one.
because I had people test it before I put it on GitHub. I don't know how long it would take.
The sophisticated version of the question is, if you have a team that's really good
Yeah.
at doing Filegi-Sunter and the related tools that you have standardizers and things that go into that, training them to experiment with these more flexible methods, especially methods that are designed to use multiple input data sets, takes time. And the biggest barrier is developing enough practical intuition with new algorithms so that you design a fair test and you are able to make the compromises that engineering of these algorithms always requires to get them to scale, which is your claim that they will,
Sure.
but they're not going to scale right out of the GitHub package.
Well, I haven't claimed that the EB method scales well, which is why we're working on the microclustering one. But it is very easy to use because we've written, I wrote a bunch of vignettes. So it is very easy to use. And we're doing the same now with the microclustering.
You have a user community that other users can find. That's not you.
Yes. Yeah, so I mean, some people from CS are using it. So,
Yes,
no,
yes, where?
at CMU,
Let's see.
yeah. And not in statistics, yeah. So,
Well, I bet we can figure it out too.
who's using it?
How to use it.
Oh, how to use it, yeah. I mean, yeah. I mean, I got feedback that it was very easy to use.
So I'll give you a little bit more. It isn't easy to engineer into a real problem yet. That's why I'm sort of pressing you on where one would get the tools and the human input to start engineering these into use.
So for the microclustering one, though, we're using it on the Syrian conflict.
Right.
And so that's
200,000, or I got the scale wrong?
it's up now at about 500,000.
Okay.
Yeah. So I would say that's the package to wait for.
In the Syrian data sets, I just out of interest, how many duplications do you see? Like how serious an issue is it to find these duplicated records?
It's a much bigger issue in general than in all of the other data sets that we've seen. I mean, so we have very little to match on. So we only match on full Arabic name, date of death, high-level location, and gender.
How much have you noticed that, what proportion of a data has been duplicated? Can you tell us? Or, I mean,
No.
Oh, you're not? Okay, all right. Any other questions, comments?
I can talk about it offline when I'm not being recorded.
Yeah, fair enough. Chris.
Sorry if I missed this, but when you have multiple databases and you have duplications within databases. Does your clustering model differentiate in some way in terms of the within database duplication process versus the between database variation?
Yeah,
In
so
what way?
that's a great question. So the way that we think, so the way that it differentiates is the way that we think about it is in the picture, the way that we think about it in terms of the modeling. I think the picture will hold better. So what we assume here is that we assume that you could have, in order to get the bipartite structure, what we assume is that you can have a duplicate all the way across versus within. And so what we're actually doing is we're searching out that whole space. And so that's how we're getting that IJL. And so if you just collapse everything down, for example, that's traditionally done into one database, then you're potentially missing more matches. And so what we're doing is we're exploiting the entire space of that structure. And so what are the advantages and the drawbacks? So one of the advantages is the fact that we get the bipartite structure here, and we're able to propagate the uncertainty exactly. What is one of the drawbacks? One of the drawbacks is the fact that you're having to search a super high dimensional parameter space. Yeah.
So I have a quick one, and I think I know the answer, but I have a feeling that other people don't. So you've used this phrase a couple times now, propagate the error exactly.
Mm-hmm.
Could you be a little bit more precise about what you mean by exactly?
Sure. So suppose we think about a record linkage method such as Follogy-Sunter or random forests or some sort of method like that. Then what we'd like to do is we'd like to be able to understand, well, what is the uncertainty from that record linkage process? And do we know that it's 0.05 or 0.1? And do we know that with a bound, or do we know it actually exactly? And in most cases, because you're not looking at the full space here, you only know it to a bound. And it's because you're cramming everything down into a de-duplication problem. However, if you look at the full structure in terms of looking at records being duplicated across and within, you can actually look at the uncertainty of the record linkage process as an exact number. Does that answer your question, Jared?
Conditional on a model and a prior.
Conditional on the fact that your model is correct. Yeah.
Okay, I think we should probably stop
Can
there.
I just one more? So if you wanted to analyze this link data, how would this error feeding? So would this error then be able to feed into some sort of measurement model so we can accommodate,
Exactly.
compensate for the, and that's the error that we would.
Right.
We
So
looked at exactly.
exactly. So this outputs some linkage error E exactly, and then suppose you want to do a logistic regression or a capture recapture or even smaller estimation, then you just put that error into your next favorite model and you proceed. And so as Jared pointed out, it's relying on this giant assumption that your model is correct. So.
Okay, I think stop there and keep any other comments. We can have we're having a wrap up in a minute. So let's thank Rebecca again. Thank you very much.